So in the circuit in front of us, we have a 6-volt battery source that's driving a current through a load of 10 ohms. And then we're representing the resistance just in the wire itself as having a resistance of 1 ohm. So of course that's going to be in series with the load that is in the circuit. And so what we want to do is figure out what's the current in the circuit and then what is the efficiency of the circuit. And so efficiency is defined as being the ratio of the power that's dissipated in the load, so what's the useful energy versus the total power that's being produced by the battery. So we've got to start off and figure out what that current is. So of course we're going to use Ohm's law in this case, V equals IR. And so we've got to find what that equivalent resistance is. So since these resistors are in series, we're just going to be able to add them together. So our equivalent resistance in this case is going to be the sum of the wire resistance plus the sum of the load. So together that equivalent resistance is going to equal 11 ohms. And then our voltage source, 6.0 volts. So we can plug that in as well. So we've got our 6 volts times the current is equal to the current times the 11 ohm resistance. So if we divide both sides by 11 and then round off to our two significant figures that we're carrying in this problem, we'll get 0.55 amps is the current. And so that's the same current that's flowing through the wire, through the load, and then back into the battery. And so now we want to calculate the power. So power, if you'll recall from our power law, is current times voltage. So in the case of the battery, to find the power being supplied by the battery, it's going to be our 0.55 amps times that 6 volts. So the total power in our circuit being provided by the battery, if we round off to 3 sig figs, we've got 3.3. And recall that power is measured in watts. So now we have to figure out what is the power that is being dissipated in the load. So not in the wire, but in just the load. So for that, we're going to have the power of the load. It's going to be equal to, again, the current times the voltage drop across that load, so the voltage across the load, which we don't know at the moment, but we can calculate that by multiplying the current times the resistance. So what we could do is we could rethink of the power law as instead of being I times V, we can replace V with I times R, and so then we end up with I squared times R. So if we make that substitution in this case, 0.55 squared times the resistance of 10 ohms. And so now that's a way for us to calculate that load without having to take that separate step of calculating the voltage drop across that load. And so if we multiply that out, we end up to two significant figures of a power dissipation of 3 watts. So if we want to find what the efficiency of the circuit is, we're going to take that ratio. So it's going to be the power that's being used, dissipated in the load, so it's that 3 watts, divided by the 3.3 watts that's being produced by the battery. And so if we divide those, we end up with an answer of 0.91, which means we have a 91% efficiency in this circuit. In our second example, we have a battery that delivers a constant 10 amps of current, whatever the voltage across the filament of the light bulb in our circuit might be. So we have 10 amps as our current, and the power required here by this light bulb is 100 watts. So we want to know what's the voltage drop across the bulb and what should the resistance of the bulb be. So in this case, again, we're going to go back to our power law. So we've got our power equals the current times the voltage. And then of course we've got Ohm's law, which is going to play a part here. So our current times the resistance. And so in this case, since we know we're trying to figure out what the resistance across the light bulb is, so we're going to make the same substitution we did in the previous example, where I'm going to replace V in my power law with I times R. So I've got P equals I squared R, so that will allow me to figure out what that resistance is. So I've got my 100 watts is equal to my constant of 10 amps squared, my current, times the resistance. So I think we can see where this is headed. 10 squared is 100. If I divide both sides by 100, we end up with a resistance of 1 ohm. And so then with that, we can calculate what the voltage across the bulb is. So if we know we have a current of 10 amps times a resistance of 1 ohm, we end up with a voltage of 10 volts. And so that, under these circumstances, is going to be the same as being provided by the battery, since our only load is that light bulb. Now, if we said that we were going to simulate the wire resistance as being 1 ohm as well, what that mean is the voltage required by the battery. So now our battery voltage, make that a B there, is going to be the constant current that's being supplied, so our 10 amps, times, now we've got these two resistors that are again in series like they were in the previous example. So that means we now have 1 ohm for the wire, 1 ohm for the light bulb, meaning we have a total of 2 ohms. So that means we would have to see an increase in the battery voltage up to 20 volts. So by doubling the resistance, we would have to double the voltage of the battery for this series circuit.